In this video, we are going to try to write the algorithm for harshad number. The algorithm harshad takes one input n, which is a positive integer. In return, it has to give us either harshad, meaning that the number is harshad, moron if the number is moron, and neither if it's none of these. Now, what exactly is a harshad or moron number? It's a very simple process. A number which is divisible by the sum of its digit is called harshad. Now, a subset of the harshad numbers are the ones that if you divide the number by the sum of the digit, you get another number which is a prime number. If that one is prime, then we call it moron. For instance, 132. If I divide 132 by the sum of the digits is 1 plus 3 plus 2 is 4 plus 2 is 6. If we divide 132 by 6, we get 22. Now, so we know this is a harshad number. 132 is harshad. But if you look at the 22, because 22 can be divided by 2, this means that 22 is not prime, so it has to be a harshad number, which is here. Now let's try 133. The sum of the digits is 7. So 133 divided by 7 is going to give us 19. But since 19 is a prime number, we call it a moron number. So 133 is moron. Now look at the number 134. 1 plus 3 is 4 plus 4 is 8. So if I divide 134 by 8, we get 16.75. This means that it's not divisible by 8, which is the sum of the digits, so this number is neither. So this is what exactly we have to do. Get a number, find the sum, see if it's divisible. If it is, then find the division, check to see if the result of the division is prime. If it is prime, return moron, otherwise harshad. If it's not divisible at all, like 134, return neither. At first glance, this problem seems to be a little bit complicated because we have to find the sum, we have to check if it's divisible, then we have to check if it's a prime. So there are quite a few steps involved. But this is a very good example of divide and conquer. Instead of trying to solve the whole problem in one shot, we are going to try to break it down into smaller pieces, write the algorithm for those smaller pieces, and then put all of them together. So here, this is a good example of using algorithms which are not prime, but we are going to write the algorithm for those operations separately and then use them in another algorithm. The first one that we are going to write is called sum of digits. So the first algorithm I'm going to write is called sum of digits, which takes a number. Let's call it none. And it returns the sum of the digits of the number. For instance, if I pass the number 132 to the algorithm sum of the digits, is going to return 2 plus 3 plus 1 is going to return 6. If I pass 134, it's going to return 8. So let's start writing this algorithm. As usual, the first one is start. The second one, because I have to go through individual digits and add them up, I need an intermediate variable, we call it sum, to save the sum of all these digits. Because I have to go through a loop, I need an index. So I'm going to call it index or anything you want. Now we are going to start our loop. So I'm going to say if index is less than or equal to length of num, then we are going to add that digit to the sum. So I'm going to say sum is equal to sum plus char of num and index. And then I'm going to increment index by 1 to go to the next digit. And now I'm going to jump to the beginning of the loop, which is line 4. So I'm going to say go to 4. And now I'm going to end my loop here. And now I can return the sum and end the algorithm. Now, this simple algorithm returns the sum of the digits. Let's test it. That's very important. When you write your own algorithm, test it, and then you can use it in another one. Let's say we call sum of digits, let's say 134. So we go back here and we start with sum. When I call the algorithm with 134, sum becomes 0. So I'm going to write sum is equal to 0. Then the next line says index is equal to 1. The next line says if index is less than or equal to length of num. Remember that num is 134. So let me just write it at the beginning here. Num is equal to 134. Since length of num is 3 digits, and the index is 1, 1 is less than or equal to 3, right? So sum is sum plus the first digit of num. So sum becomes, the previous sum is 0 plus the first digit is 1. So sum becomes 1. The next line of the algorithm says increment 1, increment index by 1, go to 4. So I'm going to say index, the previous value of index is 1, so it becomes 2. Now 2 is less than or equal to the length of num. Num is 134, so the length is 3, which is correct. So sum is the previous sum, which is 1, plus the second digit. The second digit is 3, so it becomes 4. Now it increments num again, so num becomes 3. It goes back to the top of the loop. 3 is less than or equal to the length, which is 3, which is correct. Then it's going to add the third digit to sum, so sum becomes, third digit is 4, so 4 plus 3, 4 plus 4, its sum is 4, so it's going to become 8. Then index again is incremented by 1, so index becomes 4. It goes back to the top of the loop. 4 is less than or equal to the length of num, which is 3, which is not. It is not. And then it's going to return sum, which is going to return 8. If you add 1, 3, and 4, you get 8. So we know that this algorithm works. Now what we are going to do is we are going to look at another part of the problem, a prime number. To check if a number is a prime number, I'm going to write my own algorithm, which we call it prime. and we pass a number to it, and it's going to return true or false. If the number is prime, it is going to return true. If the number is not prime, it's going to return false. Now, the question is that what is a prime number? It's very simple. Any number is called prime if it's only divisible by 1 or itself. For instance, 19 is a prime because you cannot divide 19 by any number other than 1 and itself. But 18 is not prime because you can divide 18 by 2, by 3, by 6, by 9. So it's not a prime number. So what we have to do is, when I get a number in my algorithm for prime, I just have to check to see if the number is divisible by any number between 2 and 1 less than the number. Meaning, if I want to check to see if 19 is prime, I have to check if it's divisible by 2, 3, 4, 5, 6, 7, up to and including 18, 1 less than the number. For instance, for 18, I have to check if it's divisible by 2, 3, 4, 5, 6, up to and including 17. And return false as soon as I see it's divisible by any one of these numbers. So let's write our own algorithm for prime. So I'm going to call it prime, and it takes one parameter n. So again, we start with start. We need to go through a loop, so we are going to set the loop, but the index, instead of 1, we are going to start with 2. Remember, we have to check it's divisible by any number from 2 to n minus 1. And the next one is going to start the loop. So we are going to say if index is less than or equal. Remember, we are going to go until 1 less than the number. So less than or equal to num minus 1. Then we are going to check the division. If remainder of num divided by index is equal to 0, this means that num can be divided by index if the remainder is equal to 0. Then we know this is not a prime number. So I'm going to say return false. And the next thing I'm going to do, I'm going to end this if condition. And now, if this is not true, I'm going to increment index. And then I'm going to go back to the top of the loop, which is line 3. And I'm going to end my loop with end of here. Now, when I get out of the loop, it means I couldn't find any number between 2 and num minus 1 inclusively to divide num with that number. So this means that the number is prime number. So I'm going to return true. And I'm going to end the algorithm here. So again, this is another simple algorithm to check to see if the number is prime number. It's going to start from number 2, and it's going to go to num minus 1, and it's going to check to see if the original number num, the input is num. If the input is divisible by the index, if it is, then I know it's not prime, so I'm going to return false. Otherwise, I'm going to go increment index to go to the next number and go back to the top of the loop and continue this process. When I get out of the loop, it means that I couldn't find any number that I can divide the original number with. So this means that the original number has to be prime. Now let's test this one before we continue. Let's go with, let's say, prime 7. The first, when I call prime 7, num becomes 7. Then index becomes 2. Now we are going to say, is index, which is 2, less than or equal to num minus 1? Num minus 1 is going to be 7 minus 1 is going to be 6. Is 2 less than or equal to 6? Yes. Is the remainder of num, which is 7, divided by index, which is 2, is equal to 0? 7 divided by 2, the remainder is not 0. The remainder is 1. So it goes out of here and goes here. Index becomes 3. Now it goes back here. Is 3 less than or equal to 6? Because 7 minus 1 is 6. No. Then it goes here. Now it checks the remainder of num, which is 7 divided by 3. The remainder is going to be 1 again, which is not 0. So it goes back here and increments index by 1. So index becomes 4. It goes back to the top of the loop. Again, is 4 less than or equal to 6? Yes. Is the remainder of 7 divided by 4 0? No, because the remainder is 3. Then index is incremented again. So index becomes 5. It goes back to the top. It is 5 less than or equal to 6? Yes. Now, is the remainder of 7 divided by 5 is equal to 0? No, because the remainder is 2. Then it goes back here. Index is index plus 1. So index becomes 6. It goes to the top. Is 6 less than or equal to 6? Num minus 1, 7 minus 1. The answer is correct. Then it goes here. What is the remainder of 7 divided by 6? Is 1. So it's not 0. Then it goes back here. Then index becomes 7. It goes to the top of the loop again. Is index less than or equal to 6? No. It gets out of the loop and it returns true, which is correct because 7 is a prime number. Now, why did we do all this? Is that it's now because we have the algorithms and we tested them and they are working, I can use it to solve this problem. Remember, we said that any number given to this algorithm, we will find the sum. I do have the algorithm now to find the sum. Then I'm going to divide, I'm going to check to see if the number is divisible by this sum. If it is not, then I'm going to return neither. If it is divisible, I'm going to find the result of division, and I'm going to check if the result is prime or not prime. If it's prime, then I'm going to say moron. If it is not prime, I'm going to say harshad. And I do have the prime algorithm too. Since I do have these algorithms, I can use them in my third algorithm. So I'm going to call the third algorithm harshad. And it takes a number num. So let's see how we can write this one. Again, we are going to start with start. Then we are going to check to see what is the sum. So let's call sum is equal to, what is the name of the algorithm here? So let's copy this one. Then we say sum is equal to sum of digits num. So our algorithm returns the sum of digits. Then I'm going to say if remainder of num and sum is equal to 0, then if the remainder is 0, Then I'm going to call another operator div, which is going to be num divided by sum. Because I know that num is divisible by sum, I'm going to assign the result to div. Now I'm going to go and I'm going to check if div is prime. I'm going to say if prime div, then I'm going to say return moron, because the result is a prime number. Otherwise, I'm going to return harshad. Nine, and I'm going to close my if, and then I can close or I can use else here. I can use else if the number is not divisible by the sum of its digits, then I know I have to return neither. And then I can close the if, and that's the end of the algorithm. So I wrote the two algorithms here, I tested them, and now for the problem I'm using those algorithms and calling sum of digits with the num and leave it in the variable sum. Then I'm checking to see if the original num is divisible by sum. If it is not, then I'm going to return neither. If it is divisible, then I'm going to set div, a new variable, to be the result of num divided by sum. Remember, we know that it's divisible, so there is no decimal points here. Then I'm going to check if div is a prime number. If div is a prime number, then I'm going to return moron, else I'm going to return harshad. This is much easier to understand. And the reason we could do that is we use the divide and conquer method. Now let's just check to see if the algorithm works. Let's input something like 133. So I'm going to call harshad 133. So this means num is 133, so I'm going to write num is equal to 133. Sum is going to be sum of the digits of 133. We have already tested this one, so I don't need to go through the tracing of this one. So I'm just going to return 1 plus 2, 3 plus 3 is 4 plus 3 is 7. So sum becomes 7. Then I'm going to say, is 133 divisible by 7? 19. So it's divisible because the remainder is 0. So I can say that div is equal to 19 because 133 divided by 7 gives you 19. Now I'm going to call prime 17 and 19. But I've already checked prime algorithm and I know it works. And I know that 19 is a prime number, so it's going to come here and it's going to return more, which is the correct answer.